So do you have a zigzag here that is all in the plane? Nitrogen, carbon, carbon, all in the plane, correct?
Yeah.
Okay. Then we go to this other carbon here. And what we're going to do with this carbon is we're going to put the double bond in the plane and the single bond in the plane here. Now we can't do the lone pairs on the oxygen because the oxygen, the red balls, only have 2 holes in them. So what you're going to do is with this carbon, you're going to put 2 long sticks to one oxygen here, and then another stick to another oxygen over here. Do a long stick, short stick, whatever. All right, so do you see the trigonal planar part? This part is flat. And then the hydrogen can rotate. And so this hydrogen can rotate in and out of the plane. In fact, it is rotating, but what we're going to do is we're just going to flatten it. So it's like this. And so we're going to twist the hydrogen so it's close to the double bond here. And make it like that. So this would be the glycine molecule. Did everybody get that? Yeah, it looks okay. All right, next what we're going to do is we're going to do a valence bond analysis of this. So for the nitrogen, we're going to have sp3 hybridization. How many sp3 orbitals do we have? 4, and in what arrangement? In a tetrahedral arrangement. And we're going to fill these based on the Lewis structure. And so this top sp3 orbital, what am I going to put there? We'll go off this one here. I'm going to put a lone pair there. And then this one down here, I'm going to put singles. And over here I'll put a single. And then I'll throw a hydrogen in there. And then here I'm going to bond what? A carbon. The carbon's black. I'll just make this one black. What has bigger orbitals, nitrogen or carbon? Carbon has bigger orbitals? Yeah, carbon has bigger orbitals, so let's make it bigger. Try to, not that much bigger. Carbon I'll have to do spin down, since I did nitrogen spin up, but doesn't matter. Okay, in this configuration, I have these 2 sp3 orbitals in the plane, like this. And then I have one sp3 orbital coming out, and then one sp3 orbital going in to the plane. So these, I'll just make them all spin down. These 2 coming out and going in will be bonded to hydrogen here. This one is going to be bonded to what? A carbon here. But this carbon is going to be what hybridization? sp2 hybridized. So this will be an sp2. How many sp2 orbitals do we have? We have 3 sp2 orbitals in a trigonal planar arrangement. So we need to form another bond here. Actually, I didn't give myself enough room. It's all right. I'll try do this here. This one is going to be bonded to oxygen. Unfortunately, I didn't give myself enough room, so I'm going to make oxygen smaller. Oxygen is going to be what hybridization? sp2. Oxygen has smaller orbitals anyway, but we should have 3 sp2 orbitals. These top 2 are going to be the lone pairs here. And so this carbon I made spin up, so I'll make this one spin up, and then oxygen I'll make spin down. We have that bond there. So let's see the bond so far. So far I have an S, sp3, sigma or pi bond. So that's an S, sp3, pi bond?
It's a sigma and pi, right?
So the bottom part of like the carbon on the bottom, do we have like 3 down arrows and 1 up arrow? No, like that's a nitrogen carbon. Yeah.
4 down arrows. Oops. This has got to, you're right. This has got to be spin up.
Okay. Yeah, because that's balanced, right?
Yeah. Otherwise it doesn't pair up. Okay, thanks. This is an S-S sigma bond. This is an S-P sigma bond. This would be a PP sigma bond. This would be an SP S sigma, etc. What all the sigma bonds have in common is you draw a line through the nuclei. So here's the nucleus. Here we draw a line through the nuclei, and does the overlap occur within the internuclear axis, we call it? And yes, the overlap occurs here in the internuclear axis. Here, yes, it occurs here in the internuclear axis. Here's the nuclei here, we draw the internuclear axis, the overlap occurs within the internuclear axis. Same thing here, overlap within the internuclear axis. Pi bonds are different. If we bring the 2 p orbitals head on like this, then it forms a sigma bond. If we bring the 2 p orbitals like this, then it forms a pi bond. Because when we look at the internuclear axis here, the overlap doesn't occur within the internuclear axis. The overlap occurs above and below the internuclear axis. So this is what we call a pi bond. This would be a p-p pi bond. And we have another type of pp pi bond, not pp, p pi bond. We have another type of pi bond, which is a pd pi bond. D orbitals are these 4-leaf clover-like ones. So this is a D. D has 4 lobes. 2 of the 4 lobes can participate in the pi bond here. And so when I look at the internuclear axis, the overlap occurs above and below the internuclear axis. And so this would be a PD pi bond. And so we have a PP pi bond and a PD pi bond, and that's it. No others. So you don't have much choice when it comes to pi bonds. You have a lot of choice when it comes to sigma bonds because there are a lot of sigma bonds out there. Sigma bonds in general are stronger or weaker than pi bonds? Stronger. Having the direct interaction there is better than that. And so we have sp3 sigma bond, an sp3 sigma bond here, an sp3s sigma bond here. We have an sp3, sp2 sigma bond here, an sp2 sigma bond here. That's only one bond. We need a double bond. So what's the other bond here? It's got to be a pp pi bond. Because if we only use 2 of the p's, then there's a third p that's unhybridized. Here and here. And so I made all the carbons spin up. So I'll make carbon spin up, and then I'll make oxygen spin down. And so there's going to be overlap. This is the top view above the plane because the p orbitals are sticking out this way. So this is what we call the side view here. If I look at the top view of this, this is the way I draw it. I just draw it like this, looking at the top of the p orbitals and then just bonding them like this. So this are 2 ways to represent a p. For the PD, we represent it something like this from the top view. And then there's another set of lobes. We can either dot those here or just, they superimpose. And so here, the same thing, we could dot this, and they would be overlapping underneath as well. So a lot of people get this confused. They think of this as being a double bond because there's overlap a bit here and above here, but what they don't understand is the bond is formed when a orbital is overlapping with another orbital. And so this is only 2 orbitals that are overlapping. It's not 4 orbitals. And so that just constitutes one bond. And so the double bond here is going to form from the PP pi and the sp2 sigma bond. Now when we have a pi bond, what that means is it can't rotate. Because in order to rotate, we'd have to break the pi bond. So if I take the oxygen and try to rotate it, or take the carbon and try to rotate it, it doesn't. And so we say that there's no free rotation about double bonds, as well as triple bonds too, because we'd have to break the pi bonds.
Wait, sorry, could you go over again why we know that there's a p orbital on the carbon and the oxygen making the pi bond?
Yeah, let's take a look at the carbon's energy level diagram. So we have 3 sp2 orbitals. This is for carbon. That leaves 1 p orbital untouched from hybridization. And then we fill these with electrons. I have 4 electrons in the carbon. 1, 2, 3, 4. And so that's carbon. And then we look at oxygen up here. So oxygen over here. Oxygen is also sp2 hybridized. And so we're going to have our 3 sp2 orbitals. And then an unhybridized p orbital over here. Now oxygen is going to have 1, 2, 3, 4, 5, 6 electrons. 2 lone pairs up here, and then 2 singles, which I made spin down. So to make the double bond, the oxygen is going to come in here with an sp2. Right here, this sp2, and bond here. And it's going to come in with a p on the same atom and bond here. And so this makes a double bond. We have 2 orbitals on oxygen overlapping 2 orbitals on carbon. So we get that double bond here. And the same thing from carbon. Carbon's going to come in here with an sp2 electron spin up and a p electron spin up. And we form it. And so looking at it from carbon's perspective, the oxygen comes in here, forms the double bond. Looking at it from oxygen's perspective, carbon comes in here to form the double bond. Carbon has more bonds, and so the nitrogen also comes in here. The nitrogen comes in with an sp3. I make these, not nitrogen, sorry. This carbon comes in here with the sp3. And that's spin down, so that would be this arrow here. Leaves one more bond. So we have this dangling bond here, but we know what that's bonded to. What is this bonded to? So note, you can spin this, right? There's free rotation here, because if we rotate this bond here, it doesn't break it. So the overlap is maintained. And so if we rotate the nitrogen, so we can twist the hydrogens wherever, the bond is maintained. The same thing here. We can twist this entire part here without breaking the bond. That's a characteristic of sigma bonds, but the characteristic of pi bonds is you can't rotate it. And so this oxygen, we can't rotate, it's stuck. Same thing with the carbon, it's stuck. All right, then we go on to oxygen here. Let's see. We have the oxygen here. What is this oxygen hybridization? sp3. So what we're going to do is we're going to zigzag it. So we're going to put 2 of the sp3s in the plane like this. And that means one sp3 sticks out of the plane, one sp3 goes in the plane. These 2 sp3s will have lone pairs. And I got to make this one spin down to match that. So I'll make these spin down here. And then we'll have a hydrogen bonded to this sp3 here, which will make spin up. So this is the sp2 oxygen. Let's take a look at the sp3 oxygen orbitals. Probably did it in a different color. So the sp3 oxygen, we have 4 sp3 orbitals. And let's fill those here. So this will be spin down. Actually, we'll have 2 of them with lone pairs, so we'll just make them. It doesn't matter which ones you make the lone pairs. We'll just make the first 2 the lone pairs. And then both of these will be spin down here. One of these will have a carbon come in with an sp2. So we'll have a carbon sp2 come in here to bond here. And then the other one will be hydrogen S. Will come in here and bond here. And that would complete it. And so that completes it here. This is going to be the oxygen sp3 comes in here to bond. All right, completing the orbital diagrams here. This carbon is going to be sp3. And so we'll take a look at this sp3 carbon here. we'll make our 4 sp3 orbitals. And then fill them. These are all spin down. So on the left, we have a nitrogen sp3 coming in. So like blue. Let's spin up here. And then we have a hydrogen and another hydrogen coming in with spin up. And so hydrogen S, spin up. Another hydrogen S orbital, spin up. Actually, I should do that a different color otherwise. And then finally a carbon. sp2 coming in, which would be this. Actually, this has got to spin up, which will be this electron here. Are you following along? Okay. All right, then finally the nitrogen. The nitrogen's also sp3. Let's make sure it's still recording. So we'll draw our 4 sp3 orbitals. And then what do we have? We have 1 lone pair, which we'll throw in here, and then 3 singles. And then we have 2 hydrogens come in with an S. And then we'll have a carbon come in with an sp3. So this would be the valence bond picture of this. So we want to get the angles here. So what is the hydrogen, nitrogen, hydrogen angle here that you expect? 109, because these 4 balloons, to be as far apart as possible, will adopt the 109 angle. Except the balloons aren't all the same size. Single bonds are roughly the same size no matter what's bonding to it. But a lone pair is kind of a bigger balloon or a smaller balloon? Bigger. And so lone pair requires more space, which is going to push these 3 balloons down. And when it pushes these 3 balloons down, we'll just come up with a guesstimate. For every lone pair, it's going to distort the angle by about 2 degrees. So the HNH angle should be about 107. And so the HNH angle, ideal is 109, but distorted, maybe it's going to be about 107 degrees. All right, so we have one of those, and then we have an HNC angle. We have 2 of those, but they're symmetric. So the HNC angle, we'll just do 1. The HNC angle should be 109 degrees also, but we expect a distortion to about 107. And so it doesn't matter that hydrogen's a lot smaller than carbon, it's a single bond. Single bonds are going to have roughly the same size repulsions, even though hydrogen's smaller than carbon. How about the ends? Well, the other thing we note here is that this is going to be polar. This is going to be polar because when we look at the electron cloud, hydrogen versus nitrogen, which one's more electronegative? Nitrogen. So what it's going to do is it's going to pull the electron cloud closer to it. And so electron is going to spend more time around nitrogen than around hydrogen. And so this is polar. This is also polar. And carbon versus nitrogen, who wins? Nitrogen. And so this is also polar. And so what we're going to get is, we're going to get the bond dipoles that point up. And so when we're looking at the polarity here, we have a bond dipole going up this way, bond dipole going up this way, and one going up this way. And so the net molecular dipole is going to point straight up in this particular case. So these add up to this. So this is going to be polar. In other words, it's going to be delta minus on the top and delta plus kind of on the bottom. Now, the delta EN for carbon-hydrogen bonds is only 0.4. Carbon's a 2.5, hydrogen's a 2.1. And so it comes out to a 0.4. 0.4 we classify as nonpolar. So hydrocarbons and carbon-hydrogen bonds are nonpolar, because delta EN is. Hydrocarbons are compounds of carbon and hydrogen only. And so we say hydrocarbons are all nonpolar. Because when we look at a carbon-hydrogen bond, the delta EN is small. 2.5 minus 2.1, which is 0.4. 0.4 is classified as a nonpolar bond. It's just, it's not totally nonpolar. It's just got such a small delta minus and a delta plus, it's negligible. And so we call it nonpolar. Or you could call it, you know, negligibly polar or whatever. This has got very low polarity. And so there's going to be some polarity here, but we kind of ignore this hydrocarbon part. This is going to be polar here. But let's look at the bond angles here. All right, the NCC angle is what here? The NCC angle should be and so if I look at the NCC angle, I need more space here, so let me erase this. Well, it's SP3. SP3 is 109. Are there any lone pairs to distort it? No, so it's about 109. That's the NCC angle. And then we have the NCH angle. So if we look at the NCH angle, well, it's SP3 also, so it's going to be 109. No lone pairs or double bonds. And then we have the HCH angle. The HCH angle, it's right up here, will be 109. And then we have the HCC angle. HCC angle will also be 109. So all the angles here are 109. We don't expect much in the way of distortions here. Now, when we go to this carbon, we have the CCO angle. The CCO angle should be about what? (120). SP2 is 120. However, a double bond has greater repulsions than a single bond. A double bond has twice as many electrons, kind of in the internuclear region. Although pi electrons are less repulsive, and so it's not quite double. But essentially we've got 4 electrons here in the bond rather than 2. So what happens is double bonds distort like lone pairs. And double bonds are going to take up more space. So what that's going to do is it's going to widen out this angle here, because there's more electron density here. We've got twice the electron density. So we got the sigma electron density, which is here. It's going to be polarized to oxygen, so this is a polar bond here. So it's going to be kind of asymmetric. And then we have the pi electron density. The pi electron density is above the plane and below the plane. Here. And so we got that electron density there. And so we expect about a 2-degree distortion. And so we're going to guess maybe 122 degrees distorted. The same thing's going to happen on the other side. The OCO angle should also be distorted because of this double bond pushing this single bond out. And so we expect the OCO angle, ideal it should be 120, but we're going to guess it's going to be about 122 degrees. And so we have 122 degrees here, about 122 degrees here. So 2-degree expansion here, 2-degree expansion here, which means that there must be a 4-degree compression here. And so that means the CCO angle, we have to do this. This is going to be oxygen, sp2 oxygen here. This is going to be the sp2 oxygen. And then we're going to have the CCO, this is going to be the sp3 oxygen angle. Here should be 120 degrees. But when we have a circle, all the angles have to add up to 360. So if we have a 2-degree expansion here, 2-degree expansion here, we've got to have a 4-degree compression here. So we're going to guesstimate it's going to be about 116 degrees here. And so in other words, when we're looking at the angles here, this angle is going to be about 122. This angle is going to be about 122. And this angle here is going to be about 116. Distorted. Ideal, the angle should be 120. So you should know both, the ideal angle. Actually, the most important is knowing the ideal angle. This part of it is going to be polar. This is going to be polarized towards the oxygen. That's a polar bond there. This is also a polar bond here, the sp2, sp3 sigma bond is going to be polarized towards the oxygen. And this bond here is going to be polarized towards the oxygen. So this is going to be quite polar on this end here. So here we're going to have a bond dipole pointing towards the oxygen here. And that's going to make the oxygen more negative. So this carbon is going to be more positive. This hydrogen is going to be more positive. In fact, this is quite a polar bond because what happens is the electron cloud is being sucked to this terminal oxygen, which makes this carbon less electron rich. This being less electron rich is going to be in a more severe tug of war with this oxygen, which is going to make this oxygen pull the electron cloud off this hydrogen more significantly. And that's going to make this hydrogen a lot more positive than normal. So normally when we have a COH, that's like an alcohol. But this is not an alcohol. This is different. It has different properties than an alcohol. It has different properties than an alcohol because of this terminal oxygen that's bonded here. We'll talk about that in just a second. But let's first look at the angle here. So when we look at the angle, what is the COH angle? Well, it's sp3. sp3 should be 109. And so when we look at the COH angle, we expect that angle to be 109 degrees. However, we have 2 lone pairs. Each lone pair is going to be distorted by 2 degrees, and that's going to compress these two. So these 2 balloons take up much more space, pushing in these 2 balloons, and so we expect the distorted angle to be about what? These are just guesstimate. We expect the distorted angle to be about 105 degrees. So there are a couple more things I want to say about this particular molecule here. Let me redraw it here. I want to say that this is an unusually polar bond here. It's not all oxygen-hydrogen bonds have the same polarity. This one has a higher degree of polarity, and that's due to the inductive effect. Makes the COH bond more polar than expected. You know, because the delta En here is, okay, oxygen is a 3.5, hydrogen is a 2.1. So the delta En here is going to be a 1.4. And so we expect it to have a polarity based on that 1.4. However, it's not all the same because of the inductive effect. The inductive effect has this oxygen sucking electron cloud from carbon. That makes carbon, you know, carbon's normally a 2.5. What that's going to do is it's going to make carbon higher on the electronegativity scale. These electronegativities are dynamic depending on the bonding environment. And so normally carbon's a 2.5, but it's going to make it higher because it's getting this electron density sucked away from it. And as that electron density is being sucked away, what that's going to do is it's going to have a net effect here. It's going to, rather than going towards oxygen, there's going to be a bit more of a fight here. Usually people show it like this. This doesn't make sense because oxygen is more electronegative, correct? But the reason it's shown in reverse here is because there's going to be a bigger fight for the electron cloud here, which is going to result in oxygen taking more electron density away from that hydrogen, making this much more positive. And this is quite a bit different than something like this. If we look at ethanol, oxygen versus carbon, this carbon's going to take electron density away. Actually, carbon and hydrogen, carbon's just slightly more electronegative. And so it's essentially nonpolar. It's fairly even, the sharing here. And so carbon is fine. And so what happens here is the oxygen is going to take electron cloud density from carbon and hydrogen. So it doesn't have to pull as much. And so the delta plus here is a lot smaller. The delta plus here is like water. Is water very acidic? No. The delta plus here is way bigger than water and way bigger than alcohols. And so we call this an acidic hydrogen here, whereas this isn't a very acidic hydrogen. That hydrogen has very low acidity. And so this is called the inductive effect. The other way of looking at the inductive effect is by oxidation states. So oxidation states can help us understand this. What is the oxidation state on this carbon here? If we do the oxidation state is winner take all. And so carbon versus oxygen, who's going to win all the electrons? Oxygen, so carbon gets none. Carbon versus carbon, well, that's a tie, so we have to split it. Carbon versus oxygen, oxygen wins all. And so carbon only ends up with 1 electron. How many electrons is carbon supposed to have? 4. So it ends up with a +3 oxidation state. It only ended up with 1 electron in the structure. It's supposed to have 4. Okay, let's look at the oxidation state on this carbon. Carbon versus hydrogen, who wins? Carbon. Carbon is 2.5, hydrogen is 2.1. It doesn't matter that they're close. Carbon's going to take them all. However, a tie, we can't deal with. Actually, I have this drawn wrong. Carbon wins all of them. Carbon versus oxygen? Oxygen wins. And so each of these lines represents 2 dots. So that's 1, 2, 3, 4, 5. How many is it supposed to have? 4. It has 5, so it's -1. So we say that this carbon is electron poor or electron rich. This carbon is quite electron poor, which is going to have an effect of increasing its electronegativity. Electronegativity depends on the formal charge. I have a question on the test. The question on the test is something like this. What's the fluorine's electronegativity? 4.0. So is fluoride also 4.0? Now, does fluoride really want another electron? No, it's got a complete octet. If fluoride gains another electron, it's going to have to go in the 3rd shell. So this one's going to be a lot less than 4.0. It doesn't want any more electrons. It's happy as is in redox chemistry. But what if I had F+? If I had a fluorine cation, what do you think is going to happen to electronegativity? It's going to increase. It's going to be way bigger than 4.0. I mean, this is desperate for electrons here. So electronegativity changes depending on the bonding environment. That is, what's the formal charge, what's the oxidation state. And so over here, you know, yeah, carbon should be a 2.5, but, you know, it's not 2.5 in every environment. So this carbon we say is electron poor. How about this carbon here? Is it the same or is it totally different? It's totally different. Carbon versus nitrogen, who wins? Nitrogen. Carbon versus carbon, it's a tie. Carbon versus hydrogen? Carbon wins. And so let's count it. 1, 2, 3, 4, 5. Carbon ends up with 5, it's -1. So this carbon's quite rich, I mean, relative to this carbon, which is quite poor, +3 versus -1. We go over here, this is quite rich, and then let's look at this N carbon here. If we look at this N carbon, carbon versus carbon tie. Carbon versus hydrogens, carbon wins all. And so that's 1, 2, 3, 4, 5, 6, 7. Carbon ends up with 7. It's supposed to have 4. It has 3 extra electrons. It's -3. This is very rich.
What if carbon was instead of +4? Would it be more stable that way?
If carbon was +4, would it be more stable? It depends on what you react it with and what you're comparing it with. Is CO2 very reactive? Well, it depends. It doesn't seem very reactive. CO2 seems pretty stable. I mean, people are trying to get rid of this stuff. It's too much CO2, people are saying, right? And so people are spending a lot of money on this carbon credits and whatnot. California spends a lot of money on carbon credits. And that's the penalty for producing CO2. And so people are trying to get CO2 to react with that. And so is it totally unreactive? Well, what is the oxidation state here? Carbon versus oxygen? And carbon ends up with 0 electrons. It's supposed to have 4, so it's ending up at +4. So a +4 is as poor as as poor as carbon can get with respect to electrons. You can't get any poorer than that. +4 is. But what we have to do is we have to mix. You know, we do the two-pronged approach. We do theory, which is this type of stuff, with fact. And so you have to be able to interpret this. This is something that like ChatGPT can't do, you know. It can't give you a perspective. Maybe it can. I don't know how much it's grown, but ChatGPT is still not quite there yet, you know. And so there's still a need for human input here, as humans can analyze data better. And so what we do is we look, well, yeah, it's fairly stable because we exhale CO2 with every breath. You know, it's not a very powerful. What would you expect? Something that's electron poor should be an oxidizer or reducer? An oxidizer. Should be an oxidizer, but is it a very good oxidizer? So this is where your interpretation comes in. Is it a very good oxidizer? Is it like chlorine? Each breath you exhale of CO2 is like exhaling a breath of chlorine. Would you call it comparable in terms of oxidizing strength to chlorine? No, it's going to be way weaker. Is it like bromine or iodine? You know, iodine they use as a antibiotic. No, it's not a very good oxidizer. And so this is the interpretation. We know that this is a weak oxidizer, even though it's quite electron poor. But a weak oxidizer doesn't mean it's not very reactive, because if you use CO2 on metal fires, you're asking for disaster. And so it's a weak oxidizer, sure, but it's plenty powerful enough to oxidize certain metals. And so never use CO2 on metal fires. Because CO2 is powerful enough to oxidize metals. In fact, I probably should show a video of this. You can, do you know you can burn magnesium metal in CO2? There's no oxygen. So for example, magnesium burns in CO2. You don't need any oxygen because CO2 is plenty enough to burn it. And so here you have your reducing agent, here you have your oxidizing agent. And we get a fire. I have a video of this. The products are going to be magnesium oxide and carbon. This is not balanced. We'll have to balance it. And so you need some kind of perspective regarding this here. But anyway, we're trying to gain a little bit of perspective here. And so do you see, if I have a +3 carbon here in terms of oxidation state, that's going to withdraw more of the electron cloud towards it, versus having a -1, which doesn't withdraw the electron cloud. And so this bond is quite a bit more polar than this bond. Therefore, we call this a carboxylic acid. And we call this an alcohol. Two different organic functional groups. This is called an amino acid. Amino acid is kind of interesting compound because on the left side of this we have a base. It's a weak base. This is just like ammonia. Hydrogen and carbon have about the same electronegativity. And so whether I have a carbon here or hydrogen here, I have about the same delta minus. Remember, the bases depend on how big the minus charge is there. And so this is about the same basicity as ammonia because of the differences in electronegativity are kind of small. And we call these, rather than calling these ammonia-like, we just call them amines. Amines are organic bases. And so we have an amine on the left and a carboxylic acid on the right, and we call this an amino acid. I just took an amino acid this morning. I took an amino acid because there's something going around, and so this, except they don't sell this anymore. They used to sell this. It's called NAC. Look, it's a cysteine. N-acetylcysteine. And it's an amino acid, and this amino acid was, a lot of people used to take it for, if there are colds going around or whatnot. And so I was watching this video from the series. They have a series of YouTube videos that a lot of them are free, especially the health ones from MedCram. And he was recommending taking NAC. I think he was taking it, Dr. Schveld. Dr. Schveld is board certified in 5 medical specialties. And so he's talking about NAC and respiratory illnesses. So I was just taking it as preventative, but I had an old bottle of it, and then they stopped selling it because some people were taking it for COVID, and some people were taking it for COVID, and they took it off the market. But for other respiratory diseases, people were doing it. I don't know what the exact reasoning was taken off, but there are amino acids. Amino acids are the building blocks of proteins, so we can put amino acids together and make proteins from those. And so this is the simplest. So what we're going to do is we'll take a break now, and then we'll start up again after